Hi, welcome to Solving Science edition number 7. And we're looking at this beautiful thing. It's called the Hourglass Nebula, discovered in 1955 by Jesus González Mendel Cifuentes, working in the Annie Jump Cannon American astronomer team in the US. And it's a planetary nebula. It's not anything linked to planets. It's a name that's given to these remnant stars which have run out of primary fuel, and their outer shells have exploded away from the surface, leaving a white dwarf at the center region, which you can see within this stunning image, taken by these have been taken originally by the Hubble Space Telescope, but more recently the James Webb Telescope has been looking at this planetary nebula. Why am I looking at it today is we can't explain it. Science can't explain it. There's a list of 5 anomalies with this Hourglass Nebula that we can't explain, that general relativity can't explain. There's unexplained. So I'm going to go through what these anomalies are and see if we can provide any insight into them using expanse tension theory. So firstly, there's a symmetry with this nebula, which is in itself is really unusual. It's a precision that's hard to produce using random stellar mass loss, as you would expect. So the symmetry of this thing by definition is a problem. Analyzing this, there are these 2 outer lobes which look, and you can see some pictures online that look like an hourglass, but you see this tight waist in the very center, in the equatorial regions. And again, they themselves defy explanation by any mechanism or any known mechanism that we have, again, within general relativity. We have concentric rings and arcs, and the nebula contains these, and it might be explained by some kind of episodic outburst of some kind, but the timing of this in these various shells and rings is, again, unexplained. The central star brightness is unusual because it's unusually dim. No, don't say it. Unusually dim. And the question is it obscured by some dust or something? But why is that? And then the final anomaly is the white dwarf isn't at the center where we would expect it to be. It's off-centered. And that's a problem. Its offset is about 0.1 of a light year, which again we can't explain. How is the remnant white dwarf at the center of this thing not in the center of it? What's caused that? Mainstream interpretations in science, basically there's nothing. They've gone through a list of things they would check. Is there a binary companion? Was there a second star in here? Nobody's being able to find any evidence of a binary companion, a second star within this planetary nebula at all. They've looked at whether there's some kind of fast stellar wind effect that's happening that nobody's being able to find whatsoever, or any other magnetic effect which they can't find any evidence of. So at the moment, it is the Hourglass Planetary Nebula, and it's a mystery to us in science. So let's use expanse tension theory to take a look at those 5 anomalies. Well, it's actually a perfect application of a density-dependent universe. We're seeing what could be density-dependent aspects and features from this nebula. Firstly, you've got these 2 lobes on either side of a very equal symmetry. Could be a factor of a expanse tension theory density coupling, where they transition into a low dense space. You originally had a high dense star which has put out these outer shells that then transition in ETT into the low density of space, again being carried by a greater coupling to expansion, which would explain what we see with the symmetry. And then counter to that is this tight waistband, the density section, the higher density, on the opposite uncoupled state from expansion, holding itself together, explaining this tight, sharp cutoff. Now, general relativity struggles where you have any kind of sharp cutoff event. And I've seen that previously on things like star formation efficiency drop off on the edges of galaxies, which is where when you see a galaxy, they cut off and terminate quite brutally. But general relativity, being mathematical, is a nice gentle curve. It predicts they should just slowly dissipate out, but they don't. They cut off quite hard, because that's the density cutoff switch. Where you have a density change, regimes change fast. Again, counter to general relativity prediction. You've got these concentric rings that we see. Now, this thing has gone super red giant. It's gone it's gone through this change and transition over many thousands of years, and the density would have been changing over many thousands of years. Now, what does that mean? Well, these shells and these concentric rings could be fossilized evidence of density transitions from the past. Again, almost like looking for dinosaur bones to see if something that happened in the past. So it could be that a density modulation change happened at some point in the past, and then we are now seeing the fossilized shells of those. Now, in low density space, expansion would carry those away. It would enlarge them. It would carry them with the expansion of the universe. Again, leaving that central core. We've then got an off-centered white dwarf, not in the center, but shifted off to one side, unexplained. What could cause that? Again, general relativity doesn't propose a mechanism where you could shift the central core of this in any given direction. You would expect it to be centrally located. It isn't. But of course, if we had asymmetrical density in here, you could have a shift where a low density side of this nebula would create an expansion towards a low density of space, holding high density together. So there could be a shift, and again, that pull from one side or the other could be created by just an asymmetric density profile through this nebula. Central dimness, don't. Again, it could be partly shielded by a coupling driven outflow of structures where the apparent brightness would be suppressed, but we don't feel that we need to induce any particular dark, exotic, phantom natures like dark energy or dark matter to explain it. It's within the capabilities of explaining it. So, final conclusions. It could be a direct signature of an expansion field, a quantum expansion field, coupling or uncoupling based on density dependence in the universe. It might be rare that we haven't seen other hourglass planetary nebula, but again, it shouldn't be unusual. I predict we then could see many more in exactly the same way that we've seen this. So maybe 5 explanations for 5 unexplained phenomena about this, again, stunning cosmic phenomena that we see. Thank you for watching. Thank you for listening. And we're just trying to explain what we can't see. If you know anybody who is interested in science, I would really love it and appreciate it if you could share this with them. Again, the principle of science is to prove this wrong. What is it that could say actually expanse tension theory breaks down? What would that be? That's what we need to be looking for. At the moment, I apply the idea of expanse tension theory to these various cosmic phenomena, and I'm getting results and answers that say actually we can explain some of these phenomena that general relativity doesn't explain. Of course, general relativity reigns supreme in high dense regions. It's unsurpassed as a measure, but as we've seen in other videos, there's still concerns, and I have a concern where gravitational waves passing through nothing. As an engineer, I don't like the idea of that, and I do think the idea of having a field, a quantum field, a fabric would be a more parsimonious answer, and it'd be nice to find a way of plugging these ripples in space-time into an actual medium, and again, expanse tension theory would give us that. Well, thanks for watching, and hopefully I'll see you again soon. Bye bye.